Causmaecker. I don't know if it is correctly pronounced, but it is my best. Thank you very much for accepting the invitation to give this keynote speech in ESICUP. So Patrick is full professor in the Faculty of Engineering Science in the Department of Computer Science, and he is head of the Division of Combinatorial Optimization and Decision Support. We know what that is, but also member of Leuven Artificial Intelligence. That's the KU Leuven Institute for Artificial Intelligence. That's what we want to know about. Actually, this hybridization, this bridge between combinatorial optimization and artificial intelligence is well demonstrated, for instance, in two PhD theses that Patrick is currently supervising. That's one is called Optimization and Deep Learning, and the other one is called Learning-Based Optimization Methodology, in which it's basically a project that focuses on learning-based techniques for scheduling problems with uncertainty. On one hand, we have stochastic operational optimization methods, and on the other side, you have learning-based mechanisms that are introduced to make the algorithms more adaptive and robust. This is exactly why we wanted to invite you to give this talk, to understand how we can take advantage of both worlds to solve better our problems. Actually, they're not really our problems. You are a well-known expert on scheduling, rostering, timetabling, top level in the world, but you have also, at least I could find one paper on packing problems, published in the International Transactions in Operational Research, called An Improved Best Fit Heuristic for the Orthogonal Strip Packing Problem. So you are also one of us, and so you are the right person to help us to understand how we can take advantage of these methods and of the hybridization of these two worlds. Ladies and gentlemen, Patrick Causmaecker with Data Science Meets Optimization is one to help the other. Thank you.
Thank you very much, Jose, for this nice introduction, and thanks for inviting me to do this talk and to give a presentation. Indeed, I'm not used to come to your meetings and to attend your meetings, but I'm very interested by your work. That's another thing. What I will do in this talk is I'll try to frame the ideas that we are working on a little bit in a historical context, because I think that is important, and then I'll describe some lines of research that we have been pursuing in the recent or not so recent past, and also talk about some recent work that we've been doing. And while going through it, I'll show you references to related work, which is not always, well, which I think is important and interesting to look into from your perspective. And if not, please tell me. If yes, I'll be very happy to hear as well. So this is Data Science Meets Optimization is one to help the other. So we are in another working group, the European Working Group on Data Science Meets Optimization, which has been handling this subject. I'll tell you more about the history also in this talk. So what I'll be doing is to make some historical links, talk about benefits and difficulties of implementation. I'll try to show you something about algorithms, how they can be created, selected, how you can do configuration. And I'll link you to some examples, essentially. That's what I will be doing today. So with age, you start looking back further. That's what I experienced. So 1,000 years ago, science was still empirical, as we all know, and we were describing natural phenomena. But why I find this slide interesting is that it points out that the last few hundred years, at some certain point, theory became really important, and mathematical descriptions, mathematical models, which really made hypotheses and descriptions of nature, of events that happened very accurate became popular and important. And that is something that we've been doing for a while. And one could say that we kind of had to wait until our computational abilities grew. And this came, of course, with the advent of computation and computers, to see the alternative, to start looking at alternative descriptions of nature again, in a sense. It's not completely accurate, this history, I know. It is one line of thought, but there is some truth in it, I think. And okay, so today we have this idea of data exploration to unify theory and experiment and simulation, and to see how those are linked. But the point is that we can do this today from a kind of more automated perspective. So this is not my invention, of course. This was in an article by something like more than 10 years ago, and was called the Jim Gray's fourth paradigm in honor of this famous scientist. I picked up a number of quotes which are more recent, like this one from Jean-François Puget. Reports on insights found in data aren't that useful to business. The rule of data science is to enable database decision making. So the link between decision making and the exploration of data, which may seem obvious, but is not always that obvious when you're working all the time. I've got another citation here. Data are not taken for museum purposes if they are taken as a basis for doing something. If nothing is to be done with the data, there is no use in collecting any. And the ultimate purpose of taking data is to provide a basis for action or a recommendation for action. Now, those two citations are quite separated in time, because this is a citation of Edward Deming made in 1942 already. When I start looking at the history of heuristic, I browsed through it, and some time ago I came across this paper. It's a very early paper on portfolio selection, heuristic approach. And this is in the title of this paper because it was not at all obvious at that time to devise such heuristic approaches, and that shows in the abstract actually, because the authors say that the problem of selecting a portfolio can be divided into two components. The analysis of individual securities and the selection of a portfolio or group of securities based on the previous analysis. And in 1960, the authors say, up to now, the majority of writers have focused on the first part of the problem and have developed several well-accepted methods of analysis, but little attention has been paid to the second phase of the problem. Now, why do I show this and why was I surprised? Because if you had asked me at the time when I found this paper, what was the most popular thing to do about portfolio selection, for example, it would exactly be the second one. So at that time, people thought differently. I've got some other references which I think are important, because they point out that what we are doing today is not, is not that new or that exceptional. There is an algorithm. There is a paper of 1975 on automated algorithm finding, and of course, John Rice at about the same time wrote about the algorithm selection problem in Advances in Computers is this paper. So the use of a computer to automatically generate original algorithms is discussed in this paper. Okay, I've got some other historical notes which I find fascinating, but maybe not very relevant to go into detail. But the important thing I want to point out is that people have been thinking about automated selection, automated algorithm building for a very long time already. When people started thinking about designing, tuning, constructing algorithms automatically, the first attempts were actually built on, well, these well-known theories of Fisher, of course, which we all know because we do statistical analysis of our experiments, and we follow a methodology that was found at that was built somewhere just past half the middle of the previous century, this methodology was called design of experiments, and as you can see, it actually goes much further back. And people were trying to make use of the basic principles that were developed by Fisher, his famous lady tasting tea hypothesis. But when I looked at the television a couple of days ago and I saw this latest possible finding at CERN, and I mean, people commenting on it from a very different field of expertise. Actually, people in politics were talking about this this new finding at CERN and in our virology framework. The CERN people said, look, we're not very sure yet. It is only a possible finding, but we think it is important. The probability that we've actually found something is 1 in 300. That's at least how it was translated on the Dutch television. So they want much more accuracy than that, and of course we also want much more accuracy on that, on our work, and it will take some time before the CERN people come out with and can actually stand behind their statement that they found something, but it looks as if they did at this point. Okay, so design of experiments was an important source of inspiration, and I'm citing a number of contributions from that time, or a bit later even. Yes, there's this review of Iben et al. In 2011 on parameter tuning. There is this Calibra methodology, which actually uses in detail methodology from this design of experiments era, namely Taguchi fractional design and local search, well, extended with local search, that is. It could work up to 5 parameters that did not interact, so it was not very powerful yet, but it was promising. And there's quite a bit of work by Hutte and his colleagues on this subject. This is only one paper that I'm citing here. Quite early on, also F-race, a racing algorithm for the configuration of meta-heuristics, was put forward. There was, and I'm just citing a number of names. There is this Paramills that uses local search to do an optimization on systems with discrete parameters. Okay, so oh yes, this one is also interesting. This is actually combining, back in 2011 already, combining a design of experiment method with the methods that were developed by those people like Hutte, because the problem was, as you could see in the previous slide, the number of parameters, and this paper actually concentrated on selecting the most promising parameters by a classical design of experiment method. And then there was this development of I-rays by Lopez Ibanez and Thomas Stützle, and it was called iterated tracing, and that has shown to be a very important algorithm tuner. And I will talk a little bit about this in the rest of my talk. So when I say that we want to work on an integration of data science and optimization, I have this kind of setting in mind. So we are trying to support decisions, as I argued, and you can support them, of course, from an optimization perspective, which is the right side of my slide, or from a data science perspective, which is the left side of my slide. What I want to stress is that in either case, you do not often are ready with the application of one general method. You need to be ingenious, and you need ingenuity to insert. And that's what you note in all the papers, I think, that you read on this subject, that ingenuity is needed, and this ingenuity can be more or less general. Often it is linked to, really linked to the problem, as I will show in one example. Sometimes it's really ingenious in its generalization setting, but it is always, this ingenuity is always somewhere there. And I think the interaction goes in both directions. I'll try to clarify this a little bit more. If you look at the modeling from an optimization point of view, think about my very first slide on this very long history. I kind of see the parallel, although I do not want to put optimization techniques of today back in the time of the Greeks. Of course, that's not my intention. I'm one of them. I wouldn't like that. But what you see is that the modeling is really important, and to come up with a compact model that is actually, that reflects as much elements of the problem that you want to handle, and that does this in a smart way. Yeah? Sometimes, very often, the model already contains part of the solution. For me, that's kind of an effort to describe, or that resembles to the efforts that were undertaken to describe the nature and the laws of nature in an analytical model. And when you go to data science, you tend to ask more general questions. You try to discover, you analyze, you try to find rules, you try to find constraints, but you suppose those are implicit and are actually somewhere hidden in the data. You want to have correct costs. You want to know what is important. You've got a dynamical model. You've got a model, but often it is more dynamical, and it is embedded in a large amount of data, and absolutely not as clear as the models that we use in our optimization setting. I'll try to extend this parallel a little bit when we start talking about algorithms and efforts to make those algorithms more optimal. Again, when you look at it from an analytical point of view, you try to analyze the problem very sincerely, of course. You read on it, you try to formulate the requirements, you rely on experience that you have with similar algorithms. That's a bit vague, but you intuitively try to do that. You go for a kind of an algorithm in which you may be an expert, and then you do experiments to try to see whether these findings, this algorithm actually works on, and that's also important for the next for what comes in my talk, for instances. So you're interested in instances that reflect a real situation, maybe also in instances that reflect the variation in difficulty of the problems, and maybe your algorithm applies better to a certain set of instances and less to another set of instances. But very often in this algorithm building, you are concerned with a specific setting, and that kind of sets your focus on a certain kind of instances. And you compare, of course, your various attempts and try to find the best approach possible. When you go to data science, you've got you've got another setting. You've got again a large amount of data. It's not as specific as in at the time when you were modeling your algorithm. You kind of try to collect by methods which are present in the data science world, collect relevant data, relevant examples, and try to find then how your algorithm can work on those instances. And then you come to an offline or online tuning of your algorithm to the real world, let's say. So I'm not saying that the algorithm development here has nothing to do with the real world. On the contrary, I really like, as I liked 18th century physics, I really like this formulation, and I like today's physics as well. And all those developments are very worthwhile. But on the other hand, if you look at it from a data science point of view, you would like to automate this process more. You would like to have a setting where you have the data as a description of the world where you want your algorithm to work in, and you would like to have automatic methods to come to good solutions, to good algorithms. And eventually you want to develop the dynamic algorithms, because you know, or you can see in the real world that one season is not the others, that over the years the situation can change, or over the months the situation can change, or even more unexpectedly and unpredictably the situation can change, and you want your algorithm to adapt. So these are the concerns I would say at the data science side, while of course on the algorithm side you want to be as strong as possible. You want to produce solutions that are as near to optimal solutions as possible. Okay, so I think that this was the setting in where these new methods were developed, and the reasons why people started thinking about them. And one of the settings that were developed are like this. You've got a configurator, some kind of engine that is able to manipulate your algorithm in some sense. That can be in a very minimal way, just by tuning a number of parameters, but it can also be in a very significant way by changing components of the algorithm or selecting algorithms for certain solutions. And the configurator will of course need to have some contact with reality. So you've got your software, you've got your algorithm that needs to be tuned or adapted. And your configurator can actually only call this software with a certain configuration in mind. And then the software has to work on the data, on something that is representative for the data. So this is represented in this figure here as a set of instances. So you've got a number of problem instances, on which your algorithm can work. You give it a configuration and you say, okay, and what can you tell me about these instances? So there comes solution cost, and the configurator can make its decisions based on what these costs are to come to new configurations and so on. And you've got this cyclic way of tuning your software. Let me tell you about one specific project that we did along this line, actually working on iRace. And so this was, as you can see, configuring iRace are the first two words of the title of this paper. So this is actually about tuning the tuner, configuring the setting of iRace. Okay, this was interesting in its own sense, for its own right. Can we do that? Is it possible to tune? And in what sense were the parameters for iRace set optimally? Actually, kind of by intuition, by the people who developed them, of which some were involved in this work. Okay, so what you have is you've got an algorithm, you've got a configurator, and now we're setting up a meta configurator. There were already early examples about this, but what about doing this for iRace? So here you see again the same picture as I showed you just a minute ago. So we're gonna play with parameters. We're gonna give them to a configurator. That configurator has got a target algorithm, but now this target algorithm is iRace. And okay, so it could be the configurator could be anything. It could be iRace itself. It could be SMAC. It could be Paramills, whatever. So in this experiment, we went for iRace. So iRace is actually tuning itself. All right, so this is what we call meta-tuning. I'm not going into too much detail about this, but the reason why I want to show this line is, well, there are two reasons. I want to tell you a little bit about what we have been doing and what we have been thinking about. But another reason is that there is, of course, a specific problem. This tuner is a really expensive piece of software. It needs something like 5,000 runs to do only one tuning. So in other words, one experiment that the configurator can ask the algorithm to do could take 2 CPU days. But if you then apply this to itself, of course, you've got to do exactly the same thing. You've got to do 5,000 iRace runs, and that means that you need 27 CPU years. So one reason to show you this is to show you that we can actually apply this idea of tuning to the tuner itself, which I found fascinating. But another reason is that this is actually a very heavy job, and the question was, how can we handle this? So what we decided to use in this project was surrogate configuration. So we developed functions that kind of predicted the behavior of the tuner on a certain instance, which reduced the evaluation time from 2 CPU days to 5 CPU minutes. And the meta-tuning experiment went down to 7.5 CPU days, which made it feasible. Okay, so that's what we did. It was not without problems, of course, because as it turned out, and what we could see, and what actually would need some further investigation, in my opinion, That is that this development of a surrogate seemed to miss some essential properties in the tuner. So sometimes it didn't work very well. And the reason was that the predicted behavior, of course, well, missed some really significant performance fluctuations in exceptional situations. But those exceptional situations were, of course, shown and looked at by the tuner itself, and as a consequence, we could see that the tuning was not really completely optimal. Okay, so the conclusions: meta tuning on the surrogate bandwidth indicates that there is room for improvement. Well, actually, we found very different settings of the I-race parameters, which perform better, which could be shown to perform better than the original settings. So that was a positive thing. But the surrogate modeling showed a defect, and as a consequence, when we actually tried I-race in the setting that we had developed, the behavior was not always consistent with what the predictions told us. Okay, as I promised, I was going to show you, to point you to some references that you could look at if you want. So this subject was also developed in a multi-objective setting, for example, here, where correlation between objectives is studied because tuners need criteria, and in a multi-objective setting, the criteria are not always obvious. So this was subject of this paper and another paper that I will show in a minute. Okay, so that was on tuning, on this tuning exercise for the tuner. Another line of research that we developed actually with the same student was on the characterization of neighborhoods behavior in a multi-neighborhood local search algorithm. So this was some research and about a complex problem actually. We had a meta-heuristic. There was a meta-heuristic developed. It had many neighborhoods, and the question was: is there a possibility to characterize the behavior of these neighborhoods while the algorithm is running? So this is a different setting from the previous line. We had a kind of offline attempt to optimize. Well, no, it was not really offline. It was online in the sense that we were running the algorithm again and again, but we didn't look inside the algorithm. So this exercise was about, can we use a data science technique, can we develop a data science technique to actually study and understand the behavior of an algorithm while it is running. This was based on work that was very successful and has drawn more attention, I think, than the work that we did by winning the Verilog competition at the time. But what we observed was actually the process of developing it, and we were wondering whether we could have helped somewhere. But of course, we were far too slow for these people to actually meet. So the problem was the swap body vehicle routing problem, and at some point there were something like 42 neighborhoods under consideration, and this is why we started thinking about characterizing these neighborhoods. Is there a technique to say something about the behavior of an algorithm while running on a problem? So we were actually wondering whether among those 42 neighborhoods, would there be similar neighborhoods so that it could help to simplify the algorithm? Okay, so we wanted to do a clustering exercise. So my student at that point came up with a method to do that. So she defined 3 probabilities: probability of improving, probability of worsening, and probability of having no effect. So or improve, or worsen, or nothing. So you can easily see that the sum of these probabilities must be 1. So that resulted in a peculiar statistical situation for the analysis of these quantities. And then she came up with an observation of the behavior of a neighborhood in the course of the running of the algorithm. So what is happening at the bottom of the diagram is the algorithm is executing. It's starting. It hasn't done anything yet, and here it has done 100% of the work. And over the run of the algorithm, when the heuristic was applied, you could see that these 3 measures actually behave differently. So for merged root, you had a diagram like this. So the green is the nothing, the red is the worsen, and the blue is the improve. And you see that depending on the neighborhood, there is a different behavior. And so this I think was interesting, and was what triggered her. And she designed a measure to actually formalize or quantify this effect, by defining a number of intervals over the time while the algorithm was approaching its best situation, until it had found the best result. And she defined some intervals. So the easy to reach, easy to escape interval, the easy to reach, hard to escape interval, and then the very hard to reach, where you reach the optimal. Yeah? And the question was, where can I apply which of the neighborhoods better? Now, this as a clustering problem, this was not a very trivial one. As you can see, you've got instances times regions times observables, counts up to 150 dimensions. So it is a high dimensional, low sample size, because you cannot, you've got 42 individuals over 150 dimensions, and then the sample size is of course very, very, very low. So this was a problem, clustering the neighborhoods, giving these kind of observations. But she found a technique to do that, and came up with and found that the 42 problems went into 9 clusters, of which you could say that they kind of behaved similarly over the run of the algorithm. So this is the result, and there were, I'm not sure I want to go in, I can go into detail even, but there were some remarkable similarities that were observed. And when you apply this to tuning, of course, I mean, in the meantime, the people competing in the competition, in the challenge, they had come up with a very good algorithm, which actually won this challenge. And I'm not saying that this tuning exercise was not what helped them, but what we could prove is that when you use the clusters in a tuning exercise, remember this paper, this 2011 paper that applied the design of experiments to select the most important parameters for an algorithm before a tuning exercise actually started? Well, if you do the clustering, before you start tuning your algorithm, we could show that this was this would improve the behavior of your tuning algorithm. Okay, right. So this was a line of research. I want to mention this one. I was kind of hesitating whether I wanted to keep this slide because it is kind of an old one. This is work that we did also in 2013, if I remember well, on hyperheuristics. But what I want, why do I want to show this? Well, today you're still seeing papers on this setting where you've got a kind of level above a barrier. And the idea is actually that the lower side of what is below the barrier is kind of accessible for non-experts. People that are not experts in optimization can understand what is happening here, and they can play around with rules of thumb and tricks and so on. And above the barrier, this is really this is really an algorithm that should support them. And which is not meant to be open to them, because we don't want them to learn about all these complicated things. What we did at the time was to use techniques of data science at this level. And our student Mustafa Mize at the time really succeeded to make this very powerful. Of course, afterwards, his results have been improved, and you still see very specialized papers which are studying this setting in a quite sophisticated way. So, since I'm seeing these papers still from time to time, I wanted to show this slide. This is something that we started doing a couple of years ago, and that actually is still going on. It's another link, another kind of a link between a domain of optimization, on which we have been working a lot. Of course, we've done really a lot of work on employee shift rostering, mainly in hospitals, and the link with artificial intelligence that is actually made here is trying to answer this question: can we learn the constraints? In other words, can we learn the optimization problem itself? So apart from learning the algorithm, what I was talking about just a minute ago, and understanding the components of the algorithm by using data science, you can also try to think about the problem itself and try to learn the model. Can we learn the constraints? So this was a question. This was a question that was raised by Luc de Raad for one of his students, and well, this is one of his papers actually, a 2009 papers on actually doing this, showing that you can, to some extent, learn a personnel rostering problem from looking at data about how the problem in reality is being handled. Okay, so this is another reference which is also on this aspect of automatically designing algorithms. Why I highlight it here is because this is actually about a multi and many objective evolutionary algorithm. And it is a little bit about along the line of the paper that I showed just a minute ago. It is also about the question: what is actually the criterion, and can we design tuners, or can we use tuners to actually understand what the criteria are? When is a multi-objective solution a good solution? That's not well, if you have been working a little bit on this, probably more than I have, you will understand what I'm talking about. So it's not always very clear what the criterion is. You've got many options. And the question is, can we take that into account? Okay, so this is on algorithms. I want to make another link to black box and random optimization. The question in black box optimization is to develop generally applicable methods and algorithms. Why I'm raising this one is that we have in our heuristic search methodology, we've got this concept of a neighborhood. Now, why is this neighborhood important in local search algorithms, for example? It is because moving around in the neighborhood is easier. Oh, that's one reason why it is important. It's easier than moving around in the whole problem space. And one motivation to study black box problems is that people want to develop methods to optimize problems that are very expensive to compute the evaluation function. And what we think is that if you could add a little bit of expertise, this is a little bit along the same idea of this hyper-heuristic thinking. If you could add a little bit of expertise, telling people how small changes can actually be evaluated, kind of a delta evaluation. Is it possible to define this concept of a delta evaluation in a black box setting? And could that be helpful to build more powerful algorithms? So this is a line of research that that we are also trying to pursue today, and we're not alone. There's this recent paper by Kevin Tierney, among others, Ansotjeku, Selman, and so on exactly this problem. Black box functions with extreme limits on the number of function evaluations. Okay, I'm not sure about the time. I had 40 minutes and I've used already 8 minutes more, I see. Okay, I'll move a little bit forward because I had another story on recent work that we are doing. But this is actually with Jorik Jokum, who is presently a PhD student of mine. And this is work that we are doing on using a Monte Carlo tree search for combinatorial optimization. So what he is studying, I'll tell you this in very brief. He is studying how the idea of Monte Carlo methods for game playing. Well, I think this slide shows it. This was very successful for AlphaGo. Can we apply this in a combinatorial optimization settings? We're not the first ones to do this, but he is studying this. He is studying how these methods in AlphaGo explicitly can be actually moved into a combinatorial optimization setting, and is solving problems in there. And I think he's quite successful. One of the conclusions, I'll jump to the conclusions because my time is a little bit limited. I've been too slow. I've been slower than I thought I would be. So he has come to these conclusions. It works quite well. His algorithm is performing well on the problem that he's studying. But very importantly, the modifications to this Monte Carlo algorithm for game playing actually rely on the combinatorial structure. So what he does is actually taking, building or taking expertise into the setting of the Monte Carlo algorithm to make it work successfully. So here again, we need to incorporate details of the combinatorial problem itself. Okay, I've got references, you can read that. And we think that we might make this a little bit more, less hard by including methods from deep learning in our setting. But I want to stop this talk with something that Jorik in the course of his search for problems and solving them with Monte Carlo methods came across. He tried to work on the knapsack problem, and I picked this one because, of course, it fits a little bit with the conference that we are in. He started looking at the 0-1 knapsack problem, and okay, this is a problem that for which there is a very good and very strong algorithm today. I don't need to explain you what it is. It is still, well, it is under review actually at this point. But what he did was looking at benchmarks for this algorithm, and he found out that that the solvers were very powerful, except for a specific set of instances that he came up with. So this is a new set of problem instances. Okay, this is the description of it. There are 10 groups of items. Group 10 has 1/3 of the items. Remaining items are equally distributed over the first 9 groups. And group 10 contains items with small profit and small weight. So there are many small profit, small weight items. And then the other 9 groups, he modeled well, some kind of distribution for these, depending on the parameter epsilon, as you can see. The R1 parameter and the C parameter are less relevant in this talk, and a 1/2 to the power I. This is group I, so there are 9 such groups. So you see this constant is playing a role, but this epsilon also plays a role, because it turns out that if you look at the execution time of the most powerful algorithm for knapsack, for the 0-1 knapsack problem, it shows that it is really very critically dependent on this epsilon. So this is a very narrow region in the instance space where the combo algorithm, which is the state-of-the-art algorithm, of course, needs much more time to arrive at the optimum. And what he could show was that his algorithm, also on these instances, comes very close to the optimum. It doesn't find the optimum, but it comes very close, but it does it 10 times faster. I wanted to show you that because I like this result, and I thought it was of relevance for your talk, and it also is of relevance, in my opinion, to another domain that I wanted to show you, and which I think is really important. This is about benchmarking and studying instance spaces. I've got some references here which you can look up. This is the latest conference at the Lawrence Center, which was on benchmark optimization meets machine learning, which was very interesting and was all about studying benchmarks for problems. There is the Matilda website run by Kate Smith-Miles and her colleagues on instance space analysis, where you can find instance spaces for many algorithms, and there are some papers, as you can see, which you can look up if you want. I think this is really important, because what you encounter when you start analyzing your algorithms is that you actually analyze them over a data set which should be relevant for your application, or should actually contain problems of very different nature. And this is actually what all these studies are about. And I think a lot is to be done there. I think we've got very good. It has already improved very much. We are using good benchmarks, but I think this systematic study also was important to mention in this talk. All right, so if you want, please come to the Data Science Meets Optimization workshop, where a number of these subjects are being discussed every year. This year we will have the stream at, oh, what happened? We will have a stream at Euro. We will have a DSO workshop at the ESICUP conference, and we will have something else, but I lost my, I hope I didn't lose you.
Oh, we are here.
Okay. This is the end of my talk, Jose. I'm sorry to have run out of my time.
Thank you very much. Well, time for a couple of questions. Volunteers, I have just one moment. Happily, we have many participants to have track record. So probably the first person that raised the hand was, well, everyone, Julia.
Thank you. Thank you, Patrick, for a really interesting talk. And I think this interaction of data science and optimization is really fascinating. So my question is around your thoughts and experience about whether when we try and optimize, well, so you've talked about examples where you've optimized parameters within the algorithm that's set using data science, but also use data science to kind of learn more about the actual sort of problem and the constraints and this sort of thing. Whether there's any risk that we lose the generalizability of our algorithms by almost making them so focused and efficient that we could miss out on areas which are maybe outside of the kind of data that we're using to learn from.
Yeah, well, I hope I understand your question well. If you look at my last slide, the last subject that I raised, that is to look at instance spaces. What you notice is that different algorithms behave well in different regions of this instance space. So what I think, I really believe that both lines, which I tried to describe in parallel in the beginning of my talk, of developing very strong algorithms and looking from the data science point of view, which algorithms for which parameters are performing best on which data are really very important. And I'm not sure I understand your question well. If you work on a specific problem for a specific application, of course you're going to extract the example problems from that application area. And when you start developing your algorithm, you have a brilliant idea, and then you try to find out whether this idea works in this particular situation. And it may work or it may not work. So you're actually working on a specific situation, but it has general value because you're developing powerful ideas for that specific situation, which occurs, which is there. So I'm not sure. I think we are winning in generality by putting it in a more general framework, and we need to focus. We will keep focusing because we really want very, very good results.
Thank you.
I have another question that is in the chat from Mauro Russo. He asks if you can explain on slide 22 how to detect the exceptional cases for which the surrogate strategy has determined a loss of performance. A very detailed and technical question.
Yeah. Okay. I'm not sure I'm going to be very accurate in my answer. What happened was that we noticed that the performance of the algorithm that we actually developed, that was generated, the setting of the algorithm that was generated by the tuner, did not always match the predictions. So the predicted behavior was not always the same. We could find instances where it did behave quite differently. Although overall the behavior was quite good. So we had a statistical measure and okay, predictions were not that bad, but we discovered that sometimes we missed properties of algorithms. I think this subject really deserves more exploration. It was clear for us that there were exceptional cases that we had missed in our circuits, but I don't think we were as far as quantifying this.
Thank you. Any further question? Okay, maybe I can end with a I don't know if it is a question, Patrick, but it's the following. I think that, well, and we have to keep in mind that, as George Box stated many years ago, all models are wrong, some are useful, in the sense that all models are approximation of reality, and data science, optimization, we are always working with approximations of reality. But having this said, the biggest problem of optimization models, and now I'm talking about solving the models until the optimal solution. So not heuristics or materistics, but pick a model, you solve it, you have the optimal solution. If the instance is small, if it is a small problem, a simple problem, you can do it. You have a certificate of optimality, and you are done. The problem is that when size increases, the problem becomes more and more complex, and you have the time limit that prevents you from using the model to solve more difficult and bigger problems. So it's not scalable in time. When I look at approaches based on learning strategies, what I see is that what I'm not sure is until which point those strategies are scalable regarding different problems, in the sense that every learning process, you learn what you are taught, basically. As a person, as an animal, as an algorithm, you have an input, you need an output, and you have a learning process. And what we expect is that later on, with different inputs, you generate outputs with the same quality of the previous ones. But you need good examples, you need good outputs. So, and how can you somehow scale these techniques in order to be able to provide better solutions, even for problems that they are not aware of? I don't know if I was more or less clear about my question.
Yes, of course.
Meaning that the learning process depends on the professor. We know that.
Yeah. Yes. But it's a very good question. Yes. What I see in the methods that, and as you say, what I see in the methods is that they learn by comparison. They compare approaches. So you've got algorithms working at that scale, and you compare them, and from that you try to learn a predictor of which of the algorithms, of what setting of the parameters or whatever is the best one for that. Well, a predictor that does that for you. And of course, I mean, that predictor is not more than what it says it is. It is a predictor. It can be false. Yes, definitely. The scaling problem. I remember. Well, it is handled to some extent. There are predictors that use. There are experiments. I'm trying to refer to find the. It is quite an old paper that tried to make predictions indeed based on the behavior of exact algorithms, to use this prediction to select approximate algorithms for larger problems. So this kind of yeah, this exists, and it was about, okay, which exact approach is working better here, better in the sense that it, in a short time, it realized something. It of course did not solve the problem because that was impossible. And based on that prediction, it came up with an advice for using a heuristic approach. So this kind of things, yes, but you, it's the professor that is teaching you. That's
well,
you're
but,
not yet further than that. No.
Don't take me wrong. I have some years ago with Albert, that's here in this meeting, in this PhD, about trying to, let's say, predict in a strip packing problem, rectangle strip problem. We like to predict the length of the cutting pattern.
Okay, that question, I see, yes.
But by the end of the day, the best we could do was to predict the length of the pattern given an algorithm, so with the bottom left, whatever. So because we could train the set, we trained the predictor for a specific heuristic, but in order to train the algorithm for any heuristic, well, this is why I raised the question, and I think this is very, very interesting for us, because actually cutting and packing, and I ask my colleagues to contradict me if they don't agree, but cutting and packing problems have a huge problem regarding other combinatorial optimization problems. The relaxations are usually very, very bad, and it is very hard, even linear relaxation, to have good bounds. If we had better bounds in our field, we could solve problems orders of magnitude bigger than what we currently are able to solve. So anything that helps us, that can provide us some bounds to guide our search methods and our optimization methods would be great. And I think there is room there for artificial intelligence and machine learning techniques to help us to provide better bounds. I think this is the main, I trust this will be an important focus of research in the following years, because that's what we are missing, good bounds.
Okay, thank you.
This is not my talk, it's your talk, sorry.
No. But I think it's a very interesting suggestion. Now I understand it better, because I think I misunderstood your question. Yes,
no,
indeed.
Okay.
Indeed. And very often the predictions are linked to the methods. I mean, are restricted to the methods that you're using. You can not often do very much better until now. Who knows?
Until now. Patrick, thank you very much for this enlightening and challenging talk. We'll keep several take-home messages from your talk.
I'm sorry, I had not more applications for you.
I think that people have your email and they will get back to you. You can trust this group to do that. Thank you very much once again for availability, and I'm sure that we'll keep in touch. The Euro working group led by Julia on cutting and packing, and the working group on optimization meets data science. We have a lot to do together. Thank you once again. Julia, the floor is yours.
Oh, thank you. So I think we'll have a break now. Shall we take 10 minutes? So come back at 20 past? Is that